chemistry as we begin Unit 3, which is going to cover the history of the atom, atomic structure in the periodic table, and a little bit of nuclear reactions to the extent that the wonderful Texas education authorities have asked us to instruct you upon. As always, if you're catching us on YouTube, feel free to click on the link just below this video that will take you to these slides that we are utilizing to instruct you today, along with your own copy of notes that you can fill out along the way. Either way, this is a journey of time because we didn't always know everything that we do now, of course. So let's begin in 400 BC. Wow, long time ago. Just a little bit older than you, huh? Just a little bit. Here we go. Democritus of Abdera, a Greek man, theorized that everything that we can see, touch, feel was made up of the same basic component. And he said that this same basic component is as small as it could possibly be, and it's indivisible. And so, therefore, indivisible translated in Greek is atom, which is why he theorized that everything is made up of the atom. Right? If you look him up online, you get really beautiful pictures as such. But you also get not so beautiful pictures. So who knows what this Democritus was looking like? Who knows if he could actually pull on the front of a magazine? Who knows? And then we're going to fast forward all the way to 1803, where John Dalton, who I call him Daddy Dalton as he's known as the father of the modern atomic theory, basically compiled all of the general ideas that all chemists and scientists agreed upon in that given day, and put them into one list. And he gets all the credit for it, even though everyone else had pretty much agreed on it as well. But anyways, number 1 and number 2, the reason why they had these little asterisks next to it is because they're actually incorrect. Okay? And through our discussion, we are going to learn why they are incorrect. But it's very important to note what he theorized back then and where we corrected them along the way. So number 1 is that all matter is made of indivisible atoms. And the thing that you want to hone in on there is the indivisible aspect of it. Yes, everything is made of atoms. However, they are certainly divisible, and we'll talk about that. Number 2, all atoms of the same element are identical. There is $1 million word that we're going to learn later on in this video known as isotope, and that is going to prove that not every atom of the same element is identical. Not every atom of hydrogen looks the same. Not every atom of gold looks the same, and we're going to talk about that. The atoms of any one element are different from those of any other element. Now that is certainly true. Different elements are obviously different from one another. It's just the part that's an asterisk that we're going to focus in on. But he had a couple more points as well. Number 3, atoms of different elements can physically combine, mix together, or can chemically combine with one another in simple whole number ratios. That is a very fancy way of saying half of an atom is not going to get with half of an atom. We're always dealing with whole number amounts of atoms. Okay? Water is H2O. It's not going to be broken down into H1O.5. It doesn't work that way. So it's always whole number ratios. And that is the essential aspect of the law of definite proportions. However, there's a little sub rule here. Elements can get together in different ratios. So look at this example right here. 1 nitrogen plus 1 oxygen can form nitrogen monoxide. However, we sometimes also see 2 nitrogens getting with 1 oxygen, dinitrogen monoxide. We can also see nitrogen and 2 oxygens getting together, nitrogen dioxide. These same 2 elements are getting together in different ratios, hence the name law of multiple proportions. So really point number 3 is sort of 2 different laws, law of definite proportions and law of multiple proportions. Either way, just kind of basic terminology you need to remember. And then number 4 is kind of the Captain Obvious statement of this whole thing. Chemical reactions occur when atoms are separated, joined, or rearranged. We already had a pretty good idea of that, but you had to include it in this modern atomic theory. So, as we said before, number 1 and number 2 have flaws, and we are going to discuss in further details what that is. But let's start off with some drawings of what the atom looks like right now. Now, you've probably already learned about the structure of the atom a little bit, the different components of it in middle school. And so that's why you have a little more knowledge on the subject than Daddy Dalton did. But as of right now, an atom is just a ball. There's no other pieces to it. Atoms just make up everything. Atoms obviously are these different elements, and obviously these elements look a little different from one another. But if you look at the nitty-gritty details of it, they're balls as of right now. And so that is the Dalton model. It's kind of hard to distinguish one element from another, but here we are. And so let's move on. What are these different pieces that we now know are included in the atom? What are known as subatomic particles. And the words that should be sticking out in your mind right now are the proton, the neutron, and the electron. But at this point in time, we don't know about any of them. And so now we are going to look at the important people in history that discovered them, and we're going to look at how they discovered them as well. So we're going to fast forward a little bit later, and we're going to go to England. Sir William Crookes. He's not the important guy here, although he invented the device that our first important name after Daddy Dalton that we're going to hone in on here. Sir William Crookes invented what is called the cathode ray tube, which is it's a tube that traps gases in it, and then you can inject electricity into it, and we can study the behavior on how the gases are responding. Well, Sir William Crookes didn't really do anything with it. Nothing to note. Not that I know of, at least. And then there is J.J. Thomson. Not with a P, J.J. Thomson. It's not meant to have a P there. You might be thinking it's supposed to be Thompson. J.J. Thomson said, "Hey, you know what, Mr. Crookes, can I borrow your tube? I'd like to test something out here." Well, what he did is he filled it with, I believe it's helium gas on the inside, and he injected with electricity, and he had plates on either side. And what he noticed is that when electricity, a current was running through them, that the gas was drawn towards the positive side. The gas was drawn towards the positive side. Well, what does that mean? Well, Paula Abdul in the 1990s came out with a beautiful song known as Opposites Attract. 2 steps forward, 2 steps back. We come together because opposites attract. And it's a chemical theory. Who knew that Paula Abdul was a chemist in her off time? Who knew? Right? Opposites attract. If something is being drawn towards the positive, then that means that there's something negative in there. Now, it was understood at this time that the atom was just a neutral charge, that there was nothing to it, right? Maybe it was neutral. There was no net charge anywhere in there, but this experiment obviously indicated otherwise. So Thomson said, there's something negative in there, something that's sort of separate from the rest of the atom, because it was individual components of these atoms that were being drawn towards the positive plate. And so he revised our Dalton model, which was, as we saw, just a round ball. And he would always think back at he walking uphill both ways to school in the snow in the cold, cold winter of England. And he would come home to Mama Thomson, and she'd have his favorite warm treat waiting for him, plum pudding. And so what did he do? He crafted his model after his favorite meal that his mother would prepare, the plum pudding model. And how it works is this whole bowl, this whole shape here, is the pudding. And the negative itty-bitties that are inside that are now known as electrons are the plums. And so what was theorized at this point in time was that the entire atom itself was positively charged, and that the negative itty-bitties were sprinkled inside, the negatively charged plums. So it wasn't theorized at this time that there were positively charged components. It's just that the entire thing was positive. And you can see that there's different ways to indicate this. Okay, so if you were asked to draw the plum pudding model of a certain element or certain atom, you can indicate it a variety of ways. You can say, hey, this whole thing is positive. Just draw an arrow to it and say, hey, by the way, it's positive. Or you just put a bunch of positive itty-bitties in there. Now, if you circle them, they're going to kind of look pretty similar to electrons, which, of course, we know about what protons are. We're going to learn about where they were discovered and when they were discovered here in a little bit. But as of right now, they don't know about them. So if you're including something that looks like protons in your model, you're absolute. So at this point in time, we only know about what the electrons are. We don't know about neutrons or protons. So electrons were the first subatomic particle discovered. And before we move on to our next subatomic particle, it helps to know a little background to the experiment that we are going to learn about here. And it's kind of a cool story. Henry Becquerel, French guy, I like to say Becquerel, accidentally discovers radioactivity. He was a big rock guy. And I don't know what the exact story is. I just like to imagine that he's in one of those safari hats, and he's roaming through a desert, and he trips on a big rock, and he goes, hey, that's mighty cool. I'm going to go stash that rock in my desk, and I'll show it to my fellow rock aficionados at the next rock club meeting. But when he came back to his desk, a few weeks later after storing the rock in there, the rock looked a little bit different. It had gotten a little bit smaller, and there was this film that had gathered on everything in his desk. This rock was radioactively decaying. And we'll talk about radiation here a little bit later on in this video when we talk about nuclear decay and whatnot. But we do need to know about 3 different types of radiation, 3 main types of radiation. Alpha radiation, beta radiation, and gamma radiation. And we're going to talk about this in a whole lot more detail in the nuclear portion of this discussion, but here we go. Alpha radiation is the largest out of these three, and it consists of what they say are positive helium nuclei. And the reason why is because they have 2 protons within them. And if you look at the periodic table, I know we haven't actually talked about the atomic structure yet, helium has 2 protons in its nucleus. And so, because this thing has a mass of 4 and a charge of 2, it lines up perfectly with what helium is. Beta radiation is a little bit smaller. In fact, it has no mass, and it has a -1 charge. So essentially what it is, it's the ejection of electrons. And then gamma radiation, which is what Bruce Banner used to make himself into the Hulk in the Marvel movies, if you're into that sort of thing, it has no mass and no charge. But what it essentially is in real life is it is an X-ray. And X-rays it's just straight energy. And if you're exposed to a lot of that energy, you can get very, very, very sick. And so this is why when you're at the dentist's office and you're getting your X-ray once a year, it's why your nurse puts the lead vest on you and leans out the door whenever they're hitting it on. Because imagine, a 30, 40-year career doing those X-rays, 10 times a day. That's a lot of radiation you're exposing yourself to. So that when you retire, you potentially going to get very sick. So let's look at these. As we said, alpha is the largest, which is why it can be blocked by the most simple of objects. It can be blocked by the clothing that you're wearing, can be blocked by a sheet of paper, whereas beta has a little more penetrating power. It's a little bit smaller, it moves a little bit faster, moves with more energy. And so it takes either a couple inches of wood or a thin sheet of metal will stop it. But gamma can go through everything that alpha and beta get stopped by. It takes a few feet of concrete or a few inches of lead to stop the gamma radiation. Hence why you wear the lead vests when you're getting your x-rays done at the dentist office. And so for those aspiring engineers out there, I've got a little question for you. And this was on an application for an engineering firm I saw a couple years back. You're given 3 particles, an alpha particle, a beta particle, and a gamma particle. You have to eat one, put one in your pocket, and put one in a metal trash can. Which one do you put where and why? Think about it. If you said eat the alpha, it can be stopped by a sheet of paper. Well, that's exactly why you would die. You do not eat the alpha particle. For if you did, it would just be pinballing around inside of your body, stopped by every surface, just in hitting it with a lot of energy, ravaging everything that it comes into contact with. And it can't get out. So it's just going to continue to ravage the insides of your body. So we certainly do not eat the alpha. Well, if you say you eat the beta, it's sort of the same story. I would say that all of the surfaces in your body combine to be more than a thin sheet of aluminum foil. Therefore, the beta can't get out either. And you're saying, but you said the gamma is kind of threatening. Gamma can go through a whole lot of stuff. Precisely. And the moment you put it in your mouth, it's probably not even going to go down your esophagus. It's probably going to go straight out the back of your skull. So the point of eating the gamma is because it gets out of your body instantaneously almost. And so what you're going to do is you're going to eat the gamma. You're going to stick the alpha in your pocket because your Calvin Klein denim jeans are going to stop it. And you stick the beta in the metal trash can because it can't get out. And that is how you get your job at the engineering firm. So this all helps to know, we need to know this background in talking about our next important guy in the atomic history. So we've got Daddy Dalton, we've got J.J. Thomson, and now we have Ernest Rutherford. We're in 1911, just over 100 years ago when this video is being made, that Ernest Rutherford uses what is called the gold foil experiment to discover the nucleus. Doesn't actually discover the subatomic particles within it, but discovers the nucleus. What does he do? He takes a cannon that is firing those alpha particles. Those alpha particles you just discussed, the ones that can be stopped by the pockets of your genes, the alpha, the helium nuclei, they have a mass of 4 and a charge of 2, but it's a positive charge of 2, and that's very, very important here. And he's firing it into this chamber that houses a gold foil sheet here in the middle. And most of them, as they theorized, flew straight through. They expected the atoms, the alpha particles to fly straight through. However, what was unexpected is that roughly 1 out of every 8,000 shots that he fired, they ricocheted in very, very, very hard directions. Large angles. Well, that means they had to have hit something very, very dense. And not only that, because they ricocheted, that indicated that they did not want to be next to each other. And because I'm firing something that's positive, and whatever it came into contact with it didn't want to be next to, we have to think back to that Paul Abdul theory. Two steps forward, two steps back. Opposites attract, but like charges repel, which means whatever this positive particle was coming in contact with was also positive. So now we have a new detail to include in this atom. It was very difficult to hit this target somewhere in the middle of the atom because it was only one out of every 8,000 shots that did it. This guy was putting in a lot of reps in this experiment. Only one out of every 8,000 shots hit this target in the center. And to put it in perspective just how small the nucleus is, if you're going to take a football stadium, let's just say it's your standard high school football stadium, which for some of you that's very small, for some of you it's very large. For the school that we come from, that's pretty large. Just talk about any football stadium. It doesn't change it too much. Talk about the Dallas Cowboys, Jerry World Football Stadium. The nucleus is the equivalent of a golf ball sitting at center field. And everything else, the field, the goalposts, all of the stands and the bleachers, those are all the cloud of the nucleus. That entire stadium is one atom, and the nucleus is a golf ball. So this is a small target that he's hitting, which now you can understand why it took 8,000 shots to get there. But this small target that's in there is so incredibly dense and very obviously positively charged that now this ain't no plum pudding that we're working with. That positive charge is not throughout the atom. It's within that small center. Nucleus has all of the positive charge of the atom within it and is very small and very, very dense. So Ernest Rutherford discovers our nucleus. Very, very cool. And we can kind of see more of a visual here, because imagine the gold foil plate. It's billions of atoms stacked on top of each other in the rows, right? And so he's got lots of different nuclei that he could be hitting, but it's still so small that it took a very, very long time to hit. It took lots of reps. So now with our new revised model of the atom, no more plum pudding. Okay? That positive charge is in a nucleus. But do not indicate neutrons or protons. We haven't discovered them yet. So far, we have the negatively charged electrons and we have the positively charged nucleus. Nothing else. Okay? So before we get to our most modern model of the atom, we're going to talk about Niels Bohr. And Niels Bohr sort of piggybacked off of what is called the quantum model for light, which is essentially absorbing energy, releasing energy, absorbing energy, releasing energy, and said, you know what, let's just make that the model for our atom. We know about the nucleus being in the center. We know about the electrons on the outside. Let's just say that they fly around in perfect circles. They absolutely do not. I know you drew Bohr models in middle school. You probably did. And whereas it's very good at showing you how many of each piece there are in there, it's not accurate for what the electrons are actually doing. In fact, it is only accurate for the element hydrogen, because hydrogen typically only has one electron flying around on the outside. Therefore, of course, it's going to be flying in a perfect circle. It's just like the moon orbiting around us, the Earth. And so this is 1913, where we have the Bohr model. However, not typically going to have you draw it this way because it's not very accurate. Then we move on to our last character in history that we care about here, James Chadwick. And another name for James is Jimmy. And what did Jimmy do? Jimmy discovered the neutron. And yes, this is where the name of the Nickelodeon show Jimmy Neutron does come from. Are you going to eat that croissant? In 1932, James Chadwick discovers the neutron. We're not even asking you to know how he did it. We're simply asking you to understand that Chadwick discovered the neutron. And the way that I always remember it, Jimmy Chadwick, Jimmy Neutron. Okay? He discovered the neutron. So now, also in this year, 1932, Ernest Rutherford does go back, revises his gold foil experiment, and actually discovers the proton as well. So in 1932, we get all of the different subatomic particles gathered in our atom, and now the Chadwick model, even though it could have, just as easily been called, the modern Rutherford model, whatever, has all of the components in it. If we ask you to draw the Chadwick model of an atom, you will have electrons, protons, and neutrons. And of course, your protons and your neutrons must be in the center, in the nucleus, where they are located, okay? And the electrons are floating around on the outside. So now, let's put all of this together, our subatomic particles. Your protons start with a P. They have the positive charge, and they are considered to have a mass of 1 atomic mass unit. And we'll talk about what that means here in a second, okay? Electrons have a negative charge of 1, the exact opposite charge of proton, but we say that they have no mass. because in actuality, it's about every 1900 electrons that equals the mass of one proton. So just for our argument's sake and for our ease of conversation, we're going to say the electrons have no mass in this course. And the neutrons, in the name, are neutral. They have no charge, but we say that they have the same mass as a proton. So that's all of them. And now let's talk about where they are located. Once again, the nucleus super, super, super small, a golf ball sitting in a gigantic football stadium at center field. And yet, because it has the protons and the neutrons all smushed in there, very densely packed with one another, the protons and the neutrons contribute to all of the mass. Therefore, the nucleus takes up essentially zero of the volume of the atom, and yet occupies 100% of the mass as far as we're concerned. Whereas the electron cloud, where all the electrons reside, it's the exact opposite. It's all of the volume of the atom, and yet none of the mass. So we're going to have a few other theoretical conversations before we actually get into our atomic structure questions that we're going to run into. And then we're going to solve those out on the board for you. But before we do that, before we have to answer any questions with it, we need to know what the heck we're dealing with. First of all, the charge of an atom. And the charge of an atom in this course is typically neutral, which means that the positives and the negatives are canceling each other out. I've got the same amount of protons as I do electrons. That's normal. However, electrons are the only thing that can move in and out of atoms. We'll talk about why that is a whole lot later on in this course, but just think about it. They're on the outside of the atom, so they're most readily accessible. And so, if the electrons are moving in and out, therefore the balance of the charges can be thrown off. And so there's a couple of terms here with this, right? If an electron leaves, if a negatively charged subatomic particle leaves, then now I've got more positives than I do negatives. Therefore, I have a net positive charge. And if I gain electrons, therefore I gain more negative charge, then there's a net negative charge. I have more electrons than I do protons. Whichever one outweighs the other, that's the charge that you've got. But there's a different name for each, okay? If you are a positively charged ion, an ion is a charged atom. If you are a positively charged ion, then you are called a cation. The way that I remember this is cats have paws, and cations are positive. Classic. And then, this one's a reach here, okay? This one's a reach here. But I will say my Louisiana-based colleague next door to me in my school, she doesn't pronounce it anions, which is the proper way of pronouncing it. She pronounces it anions. And you know when you're cutting onions in the kitchen before your delicious meal that you're cooking for your hot date, you're chopping up the onions in the kitchen, and what are they going to make you do? They're going to make you cry, make you feel all negative, make you feel sad. So, cations are positive, anions are negative. All right? Moving on to what identifies an element. And there's different ways that you can actually see these labeled. Okay? This is how it appears on the periodic table, right? This symbol looks fairly familiar to us. 118 of them on the periodic table. This just happens to be oxygen. Well, as it stands, what identifies an element? The identifier is the atomic number. And the atomic number corresponds to the number of protons that an atom has. If I have 8 protons, I'm oxygen. Period. End of story. There is no atom that has 8 protons and is not oxygen. All right? Here's where things get kind of spicy. This number down here, the atomic mass, this is where it can change. And so this is where you want to be thinking in your head, if protons weigh 1 and neutrons weigh 1, how can my mass not be an even number? How can it be a decimal? How can it not be a whole number? And that is a very important question that we are going to answer right now. Because the mass of an element can differ. It can change. And this is where Daddy Dalton got it wrong. This is that second point in his modern atomic theory. Not every atom of the same element has the same mass number, and that's totally okay. However, every atom of the same element absolutely has the same atomic number. But where they differ is their mass number. And I don't want to point out pictures like this to make light of any situation, but it's weight, it's mass. And so what I've got here are 2 different sets of twins. They look very similar in the face, however, obviously, very different looks in the body. Why? They're the same, let's just say person, same identity, but with different masses. And that is what an isotope is. Your mass number, aka the mass of an atom, is simply your protons plus your neutrons. So the mass of any atom, as far as we're concerned, is always a whole number. However, if different atoms of the same element can have different masses, why do we get a decimally number in the end? Well, it's because of these things called isotopes. Isotopes are atoms of the same element, different numbers of neutrons. So we can't change how many protons they have, because if we change how many protons they have, then they wouldn't be the same element anymore. Therefore, if they've got different masses, what's the only other thing we can change? It's the neutrons. So isotopes are different because they have different numbers of neutrons, and therefore they have different mass numbers. And so, why does this matter to us? Well, it's because this mass number that we see here, this atomic mass that we see on the periodic table, is not just one measurement. It's actually an average. And very, very, very smart, intelligent, brilliant people, well before our time, well before you or I are born, figured out a way to measure the mass of every single atom, of every single element that was currently known on the periodic table, and take the average of all of their masses. And so, when I see that oxygen has an average atomic mass of 15.999, that tells me that most oxygens probably weigh right around 16 as their mass number. However, not every single one of them is going to have that as their mass number. And we're going to learn how to calculate that here very, very shortly. So now, different ways to write isotopes, and we're going to do a couple of these examples here on the board. So we'll solve that for you here in a second, but let's look at a few examples. There is different ways to write it. Hyphen notation, which is a way to write specific isotopes. But the main way, the thing that gives you the most information, is known as nuclear notation. And look at it set up right here. Okay? Your symbol is the largest part of it, the X. Your mass is going to go in the top left, and the atomic number, the thing that identifies it as the element that it is going to go on the bottom left. So it's always bigger number over smaller number. And so when I'm looking over here, remember the different combinations here. The charge of your atom is based on the protons and the electrons. The mass of your atom is based on the protons and the neutrons. Okay? So when I see an atom with 4 protons and 7 neutrons, that means my mass is going to be 4 plus 7. And my charge, because I've got 4 protons and 4 electrons, is going to be neutral, because my positives and my negatives are equal. There's no difference between them. And so if I've got 4 protons, all I've got to do is look at my periodic table for element number 4, and that's beryllium. So that's why it gets the symbol Be. My atomic number is going to go in the bottom left, and the mass, as we specified, is going to go in the top left. If it is a neutral charge, you don't have to write anything in the top right. However, if there is charge, such as in our second example, notice that the protons and the electrons are not equal. Therefore, there is a charge. You must denote that in the top right. So let's look at these examples here on the board. We're going to write them with both hyphen notation and nuclear notation.
Then we're covering the different types of notations that we can write. Typically, we're going to use hyphen notation or what is called nuclear symbol notation. Either way, we got a few examples here for you. And they're always going to give you protons, neutrons, electrons, that kind of information. Maybe they'll straight up give you a charge. Either way, you need to be able to extract information that they don't provide, assuming that they give you everything that you need, and they always will. So our first example, an atom with 17 protons, 20 neutrons, and 18 electrons. If we're going to go ahead and let's just start with the nuclear symbol notation, since hyphen notation uses everything the nuclear symbol notation already includes. Let's start with the 17 protons. That tells us what element we have here. And so, if it has 17 protons, the atomic number is 17, which means we simply need to look at number 17 on the periodic table, which is chlorine. So we know what element we're dealing with here. And then it also says that it has 20 neutrons. Well, the larger number, the atomic mass of that atom that we're talking about here, is the protons plus the neutrons. So 17 plus 20 is 37 as its atomic mass. Then the last component, if necessary, is the charge. And the charge is going to be located in the top right. And what you need to look for is the difference between your protons and your electrons. If they are the same number, and they typically are, then it is a neutral atom. But in this example, I've got one more electron than I do protons. If you want to think about it mathematically, algebraically, then you could do this every time, although it is a pretty simple relationship, but your charge is simply equal to your protons minus your electrons, like so. Either way, what I think of, though, is that the proton is a positive charge, the electron is a negative charge, and I've got one more negative than I do positive. Therefore, my charge is -1. So I've got mass of 37, atomic number 17, charge of -1. You don't have to actually write the 1, it's just like in math. And then, in hyphen notation, it would simply look like this. Chlorine hyphen 37. I have seen sometimes in hyphen notation they'll include the charge kind of right here. Now that being said, when I write it, I typically don't include that, which is why I will definitely value the nuclear symbol notation over the hyphen notation because it provides all of the information and not just the mass. Hyphen notation is a really good way of telling you what isotope you're dealing with. So moving on to the next example, an atom with 22 protons, 26 neutrons, and 22 electrons. All right, so we've got our atomic number 22, all right? And so we need to know what element that is. All I gotta do is look at element number 22 on the periodic table. Happens to be my very favorite element, titanium. And titanium has 22 protons plus the 26 neutrons, which means the mass here should be 48. And my protons are the same as my electrons, so there's no charge here, so I don't need to put anything in the top right corner. So then, hyphen notation, this is simply titanium dash 48. Like so. All right, in our last example, an atom with 30 protons, 33 neutrons, and 28 electrons. So, atomic number 30. That tells me that the element is zinc. We have 33 neutrons. 30 plus 33 is 63. So our mass is 63. And I've got 2 less electrons than I do have protons, which means I'm going to have a positive charge. And yes, the correct way of writing charges is the number in front of the sign. Not like your professor's really going to care. Your teacher shouldn't care. If they do, the number should go in front. So zinc with a charge of 2+, which means our hyphen notation is going to look like so. And that's how to do nuclear symbol notation and hyphen notation.
Before we dive into the only mathematical concept that it takes calculator math, average atomic mass, we need a standard. Everything's got to have a standard. And our standard here is carbon-12. Carbon-12. They took what they say is the most important element because it's the element of life. Everything that is organic and living has carbon at its center. Carbon-12, and it's the most common isotope of carbon. Well, what they said is that an atomic mass unit, when we're breaking down these atoms into their components, and we're trying to measure it in a more simplistic way, if we take 1/12 of carbon-12, 1/12 of carbon-12, and carbon-12, when it's neutral, has 6 protons, 6 neutrons, 6 electrons. Okay? So, there's a little bit of miscalculation here. There's a little bit of assumption here. If it's 1/12 of carbon-12, well, that's not just protons and neutrons. Electrons do have a little bit of mass in there. So therefore, when I say that 1/12 of carbon-12 is equivalent to 1 AMU, I'm not saying that 1 proton is exactly equal to 1 AMU, but it's pretty dang close. And so this is why if you ever hear anyone say in another video or somewhere else saying that the relative atomic mass and the actual atomic mass are not the same, it's because they're not. But they're very, very, very freaking close. And so by all of our intended purposes in this course, they're the same. Okay? A proton is an AMU, a neutron is an AMU, and an electron is 0 AMU. We're just going to go ahead and say that an electron is massless. And remember that we mentioned that those decimal average atomic masses that we see at the bottom of each elemental square on the periodic table is an average. Because if a proton is 1 and a neutron is 1, if I'm adding up all of these numbers, it should always be a whole number. And if you're looking at it on an atomic basis, atom by atom, well then yes, it will be a whole number. The mass of one atom is a whole number, as far as we're concerned. But the average of every single atom of that element on the planet can't possibly be a whole number unless there's only one isotope. And so how are we going to do this? Well, we're going to learn how the scientists did it way back in the day. Calculating average atomic mass. Now, there are devices out there that are able to take pictures of the entire world, essentially, spectrophotometers, and based on the peaks on how you're reading this graph, it can tell you how much these atoms weigh. It can also tell you how frequently they're appearing. This is just like those questions that you were learning in middle school math where it's like, you've got 26 marbles in a sock. 12 of them are red, and 13 of them are purple, and one of them is flushed with lavender. Reach into the sock, and what's your likelihood of pulling out something that's not a pineapple? Something like that. That kind of thing. So out of all of the coppers in planet Earth, we're just going to say that copper has two isotopes here. One that weighs 63 AMUs and one that weighs 65 AMUs. And 69.71% of the time, the copper is going to weigh 63 AMUs. And then the other 30.83% of the time, and now I'm seeing that there's no way this even adds up to 100%. This is pulled straight offline. But it's going to be pretty dang close. Okay, it's going to be pretty dang close. What should this be? We'll change it here in a little bit. But either way, you know what? Let's change it. Boom. There we go. How about that? 30.29%. Now it's at 100%. And then, boom. This is just like how you calculate your grades online. Okay? And then also, let's give you a little hint here before we dive into this. If we're doing the average atomic mass of an element that's on the periodic table, what should your answer be pretty dang close to? That's right, the mass that's on the periodic table. Pretty cool, right? So you've got like an answer key to base your answer off of. However, sometimes they make up fake elements for these kind of questions. Either way, the process is very, very simple. And we're going to show you how to do this on the board now.
Next, we're going to be looking into how to actually solve for the average atomic mass, and what the problem is going to give to you is the different isotopes that are present here and also their percent abundance, how frequently they're appearing in a sample size of this element. So what we have in front of us here are two different isotopes of copper and the abundance in which they are appearing. So there's definitely more copper 63s than there are copper 65s. A couple of things to consider before you're even solving this out is, what is my answer range going to be? A lot of kids know how to do all the steps and then don't realize when they've got a very obviously wrong answer. This is an average, which means your answer must fall in between your lowest and your highest value. If I get a number that is not between 63 and 65, even if it's 62.99999 or 65.000001, I very obviously did something wrong. And if I don't realize that, then my goodness, I'm losing free points. On top of that, if nearly 70% of it is copper 63, then I'm going to assume, because I understand mathematical relationships, that my answer is going to be closer to 63 than it is to 65. If you understand these logical relationships, then you're much better off. So let's solve it out here. Essentially what we're going to do is we are going to convert this percentage back to a decimal. Just like how your grades are calculated in school. Your tests are valued more than your quizzes are valued more than your homeworks. Well, they're worth a percentage of your grade. And what it does is it converts that percentage back to a decimal, multiplies it by the average of that category, and then sums it all up. So what I'm going to do every time I get a percentage is I'm going to essentially divide by 100, which means I'm always going to move the decimal over 2 places to the left. And then what I'm going to do is I'm going to multiply my newly converted decimal by the number that it's associated with and add those together. So I've got 0.6971 times the mass of 63 plus 0.3029 times the mass of 65 that it is associated with, like so. All right? And this is the only section of this unit that you're going to need your calculator out for, so you want to make sure that you have that at the ready. So 0.6971 times 63 plus 0.3029 times 65, and we get our answer as 63.61 AMU. Your units are AMU. In measurements like this, there's not really sig figs to deal with except for really the percentages here. So I'm really going to encourage you just to provide a couple of decimal places unless your teacher's saying otherwise. But we've got another example here for you in just a second. So now we've got another example problem here for you guys, this time using magnesium, and these are true measurements of the isotopes of magnesium on planet Earth with their relative abundances. So what is our answer likely going to be close to? Well, first of all, what's the range it's going to lie in? If I get an answer that's below 24 and greater than 26, I have a 0% chance of getting it correct. On top of that, though, it's nearly 80% magnesium-24, so I'm expecting the answer to be pretty close to that. All right? So let's go ahead and go off of that information, but either way, we're going to convert all of our percentages back to decimals, which means dividing each of these by 100, aka moving the decimal 2 places to the left, and going ahead and erasing those percentage symbols. Like so. Did a terrible job of that. And boom. Next, it's going to be taking these decimals and multiplying it by the mass that it is in conjunction with, and then adding them all up. Now it's simply plugging and chugging into your calculator. We already know what our answer is going to be quite close to. And really, if you just plug it into your calculator exactly as it is written up there, then you'll be good to go. Kind of hard to mess these up. And we get our answer as 24.32 AMU.
This is sort of like an extension of when we were talking about the periodic table in Unit 2. A little more history and background to it. The periodic table is very intentionally designed, however, did not always look that way. In fact, the first periodic table was developed by a Russian, a gorgeous Russian, Dmitry Mendeleev, who his periodic laws, neither the properties and the elements, are repeating according to their atomic masses. So the properties that we see within the elements that they knew at the time were according to their masses, and that's how we organize it. The lightest element to the heaviest element. But if you look at your current periodic table, your up-to-date periodic table, you're going to see a couple of hiccups in there, where sometimes an element that appears after another one is actually lighter than another. And that's because we found a better way of doing it. We found what the true indication of the properties of the elements was caused by. And it's not based on their masses. But here is the very, very early periodic table. Notice the Russian dialect here. But this guy, so smart. They didn't even have these elements discovered, but he was just estimating. Between zinc and arsenic, there should be 2 elements, and it should roughly have these masses. And if you look at the periodic table, he's pretty freaking on the money. This guy's brilliant. And you will notice, J, before they developed, or sorry, not developed, created the most recent string of 6 elements or so in the last 20 years. They had these placeholder names. They had these weird placeholder names, and the only letter not present on the periodic table at that time was J. Yet in Russian, they use the J more frequently than the I, because this is like Jayadine instead of just iodine, that sort of thing. But very, very interesting there. But either way, Mendeleev organized the periodic table according to mass, but it was Moseley who came along and said, you know what, there's probably a better way of doing this. Okay, mass doesn't actually indicate how they're going to behave. And so, instead of organizing them based on masses, we organize them based on atomic number. And that's why the periodic table you just read straight from left to right, top to bottom, 1 through 118, the masses aren't actually relevant there. And so the modern periodic law is that the physical and chemical properties of the elements are functions of their atomic numbers, not their masses. Let's look at a couple of weird other periodic tables that I've never actually seen practically used. I've just seen their existence. Okay, here's one where it's kind of like a helix shape formation. The elements are actually going out, starting from the center and going all the way, extending out. Kind of cool. Dr. Stowe has got a weird based on their series that they're in, the period that they're in. So essentially their row, which is super unique. And we already have the theorized elements number 120, 121, that sort of thing down there. But that is all we need to know for periodic table. And the last topic of today is actually nuclear chemistry. And yes, there are facts we need to know with this, stuff that you just kind of have to memorize, ingrain into your brain, and regurgitate on the paper. But there's also a little bit of application. Okay, so, and when I say application, it is minimalist math. I would trust a third grader to do it. So we don't actually even need a calculator for this either. But here we go. Let's jump into it. And let's talk about why nuclear should be talked about. There's sort of a little debate. I would say most agree that nuclear energy is a good choice for a power source. But there are those who are against it. There's a really good TED Talk on it. Sources of power: coal, natural gas, the primary fuel that we use day to day in your vehicles, all that jazz. It's running out. It's not sustainable. It's not renewable. And it produces a lot of waste. So what are we going to do? Well, there's lots of alternatives. Solar panels being one of them. However, very expensive. I believe in the TED Talk they mentioned that if you were to power the entire United States with solar panels, it's like the entire southern half of California, Arizona, and New Mexico, and the western part of Texas would have to be entirely solar panels to power the entire United States. That's a lot of real estate and a lot of freaking money to do so. Not to mention the fact that once they become useless, once they're done and their life is over, they become nuclear waste. So you can't just toss them in the trash can and get them hauled away on trash day. So, something to think about there. Hydroelectric power, fantastic. However, how many of you have excellent waterfalls in your backyards? I certainly do not. So it's not an option for everyone, sadly. Wind power, excellent as well. However, that's a lot of real estate. You can't just put the fan blades directly next to each other with the blades, having the minimum distance apart from each other. That's not how it works. And on top of that, they're very loud. I believe the TED Talk also mentions that if we were to power the entire United States with wind farms, it's the entire Midwest. Like north part of Texas, Oklahoma, Kansas, going all the way up the entire Midwest of the United States. And there's not really room for anything else. Yeah, you can have farmhouses and small buildings on these wind farms, that sort of thing. But it would not work with our current setup, with our cities and whatnot. And geothermal energy is amazing. However, it's not just about digging to the center of the earth and then holding a Schmucker's jar up to it and spooning the energy into it. We don't really have the technology to harness it yet, which leaves us with nuclear energy. Nuclear energy, it's good. It's producing very little waste. We have the technology. However, the waste that it does produce is very dangerous, very spooky. And so what they do is they form these little concrete bunkers or steel chambers, so to speak, just below the surface, or several feet below the surface of the earth, and bury it there essentially. And it must stay locked away for thousands of years potentially. But once it's done with that, it's done. No harm done. And so I believe it's what would fill 100 train cars of waste with coal and natural gas would only fill a Coke can of nuclear waste. They would provide the same amount of energy. So nuclear is much more efficient with its waste production, that sort of thing. But either way, the waste that it does produce is sort of dangerous. It's we've all heard of Chernobyl, the meltdown that occurred there. Well, yes, accidents can absolutely happen. You'll see the reason why some of the hurricanes last year in 2019 that were so spooky is because they were directly in line with with a lot of the big nuclear power plants of our country. And the reason why is because you have to store them on good sources of water because that water is providing a lot of the cooling agents necessary to keep the temperature down. Nuclear energy produces a ton of energy, which therefore produces a ton of heat. And so it sounds kind of scary, most of these nuclear power plants are right on the ocean shore. And it's not that they're dumping the waste inside. I certainly hope they're not doing that. But it's because they need all of that water. And so if a hurricane's coming, cleanly across the top of it, you want to make sure everything's shut down properly. You're certainly not going to run the risk of another Chernobyl happening. But what are the uses of nuclear power that we perhaps have seen or done ourselves? Radiocarbon dating, for one. This is a very cool process. Carbon has its most common isotope, as we mentioned not too long ago in this video, carbon-12, but it has a couple of other radioactive isotopes, carbon-14 being one of them. And this is actually how they determine how old the dinosaur bones are in the soil, how old the fossils are whenever they dig those up. It's very cool. They know exactly how long it takes for half of whatever source you're looking at to decay, and so then it's just a simple formula. It's just a simple mathematical calculation to determine how old this thing was, when it was Roman, which is really cool. Food irradiation is not uncommon as well. There are safe ways of irradiating foods to make its shelf life a little bit longer without the potential of hurting you, which is pretty awesome. And there's just something about that irradiated milk. Coming home to a nice lukewarm room temperature glass of milk after a long day. Hits the spot, wet your whistle. It's also very frequently used in medicine. And I love this picture that's using technetium. Technetium is not a naturally occurring isotope. It's a man-made element. How awesome is that? that the world didn't have something and you needed something to fill a certain niche for you. And so you just went into the lab and freaking created it. How cool is that? So awesome. But there's various elements that are able to use this. Anything that's radioactive to a certain degree. Barium is frequently used. They're not just straight up injecting uranium into like the supervillains in the movies. Either way, why are these elements radioactive? Well, it's because the balance has not been made. Okay? There's unstable nuclei present in these atoms. And most of them are beyond element number 92. If we start at the beginning of the periodic table and proceed from left to right, top to bottom, you're going to see that in the beginning, it's one proton for every neutron, typically. But as you get a little bit further in, it takes more neutrons to balance out those protons. Why? The Pauli-Abdul theory. Opposites attract, but like charges repel. Protons are all positively charged, so if you're slamming them all into a nucleus, do they want to be next to each other? Absolutely not. And so all of this force, all of this repulsion is in there, just building, and as we add protons more and more, so we need more and more neutrons to cancel it out. So there is a sweet spot that every atom is trying to hit, and so what they undergo are these radioactive reactions in order to try to reach stability. And I think we can all relate to that. We're all just trying to get stable and happy. And so we can look at these little graphs. This is known as the band of stability. And if your point is on this little line, this band, well, then you're good to go. You're happy. You're stable. But if you're above it, if you're below it, if you're way off to the side somewhere, it tells you what type of reaction you're going to undergo. And so now we're going to learn about those different types of reactions. And this is where the little baby third grade math comes into play. Okay? This is kind of weird. Nuclear chemistry sometimes is not even called chemistry because some of the laws we've discussed previously in this course, we're going to end with what we started with. However, in these reactions, you're actually going to have sometimes elements turning into different elements. Oh my goodness. I don't know if you've ever read the book The Alchemist, which is a story of a guy who could supposedly change something, anything you wanted, into gold. Become rich. Amazing. Elements turning into other elements. What a spicy idea. What a concept. Let's begin with our alpha radiation. So this is what Mr. Ernest Rutherford was shooting out of his alpha cannon. And another way of writing the alpha particle, which here's the Greek symbol for alpha, but it has a mass of 4 and a charge of 2. What also has a mass of 4 and a charge of 2? Look at helium on the periodic table. It perfectly fits it. And so they say that an alpha particle is essentially just a helium nucleus. Out of the 3 particles that we're going to talk about today, this is the largest and it travels the slowest, which is why it has the least penetrating power. It gets stopped by paper or clothing. But either way, it is always going to release a particle with a mass of 4 and a charge of 2. That's the only thing you need to remember here. Because when I look at an example, okay, and this example is already been done for us. We're going to do another example here in a second. When I look at the example, just imagine that we can't see this right now. We can't see the right side of the arrow. Let's just say they start us off in the problem by saying uranium-238 undergoes alpha decay. If it undergoes alpha decay, well then you know one of the products is an alpha particle. And an alpha particle has a mass of 4 and a charge of 2. Well, where did these other numbers come from? Well, we're not completely throwing the rules of chemistry out the window. If we started with a mass of 238, well, then we are going to end with a mass of 238. The mass is not going to disappear. And if we started with 92 protons or a charge of 92, well, then we are going to end with a charge of 92 or 92 protons. And so then it's just filling in the blanks. So this is one example, and let's solve another on the board now.
So let's do an example of alpha decay that's not in your notes, and it really doesn't matter what you're starting with. It's the same process whatsoever. So we're going to pick a random atom here. It might not necessarily undergo alpha decay nutritionally, but as long as you understand what an alpha particle is and what it means to undergo alpha decay, then you're good to go. So let's just take a random element, phosphorus, and apply a random mass to it. Let's say it has a mass of 38, okay? Phosphorus 38. Phosphorus is element number 15, and it has a mass of 38. Undergoes alpha decay. That's all they tell you. So this is our starting point of the reaction. Well, if it undergoes alpha decay, then I know it's going to split apart into 2 different products. An alpha particle and something else that I need to figure out. Well, you need to know what an alpha particle is. And an alpha particle, always, 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 without fail, has a mass of 4 and a charge of 2. I traditionally write the helium nucleus variant. It doesn't matter which one you rock with. So now, this is very, very simple. Let's be very intentional about this. We've got mystery element X with a mass of Y and a charge of Z. And we're going to fill in these blanks here. If I started with a mass of 38, and 4 of it is right here, then what does Y have to be? Well, 38 is equal to Y plus 4. Solve it in your head, ladies and gentlemen, and you get that Y must be a mass of 34. Okay? If I started with an atomic number of 15, and 2 of it is right here, what does Z have to be? Well, 15 is equal to Z plus 2. Goodness gracious, solve it in your head, and we find out that Z must be an atomic number of 13. Now, how do we fill in what X is? This number is going to tell you what your element is. Therefore, I look at what element number 13 is on the periodic table, and I know that it is aluminum. Typically, the answer that they're looking for is this particle right here, but they could be asking for the entire product side of the reaction. That's alpha decay.
The second particle out of the 3 that we're talking about today after alpha is beta decay, beta radiation. And a beta particle has a mass of 0 and a charge of -1. What also has a mass of 0 and a charge of -1? An electron, which is why sometimes instead of this beta, you can actually see just an E for electron being written. And this is kind of a cool explanation for it. But what they theorize right now, what a neutron is they say it is the proton fusing with an electron. That's what makes a neutron. Neutron has no charge, it's neutral, so it makes sense for a positive and the negative getting to cancel each other out. However, they're fighting. And the proton says, I can't even look at you anymore! I'm tired of living like this! Get out! Get out! And the negative packs her things, the electron packs her things, and she leaves. She leaves the nucleus, and that's beta decay. So, the neutron essentially ejects the negative component of it and keeps the positive component. So the mass stays. However, the charge changes, which is why we're going to see what we see. In this example, we're going to do another example for you on the board just to make sure you guys are getting it. We're going to see a change. Carbon 14, atomic number 6, because it's carbon. It ejects something with a mass of 0 and a charge of -1. So the mass does not change. However, the positive component of this neutron stuck behind, which means the atomic number actually increases by 1, which is a very, very weird concept. But here's the easiest way of doing this. If you know what a beta particle is, if you know that it has a mass of 0 and a charge of -1, well, then we can just fill in the blanks over here. And once I get this number 7 situated, then I can fill in what this element actually is. So let's solve another on the board now with beta decay.
Now let's do the same thing with beta decay, picking a totally random element with a totally random mass. I'm just going to say titanium because it's my favorite with a mass of 50. Sure. Titanium with a mass of 50, and titanium is element number 22. And the question tells you titanium undergoes beta decay. What is the resulting reaction? Well, if it undergoes beta decay, you know it's going to split apart into 2 different pieces, one of them being a beta particle. And a beta particle, you have to know what it is. It is the exact stats, the exact specifications of an electron. It has a mass of 0 and a charge of -1. Like so. Well, we're just going to fill in the blanks, and yes, we can be super intentional with it about it again. X, Y, Z, like so. Let's go ahead and solve our Y. Y plus 0 equals 50. Class? Good! It is 50. Well done. The mass does not change. Z minus 1 equals 22. The answer is, in fact, 23. So we need to look at our periodic table at what element number 23 is. No, it is not vibranium, but it is vanadium. And there we go.
And our third type of radiation for the day is gamma radiation. And you hope and pray that a gamma radiation question occurs on your quiz or test because they are incredibly easy to remember. It has no charge. It has no mass. So now you're thinking in your head right now, what happens to the original atom that is undergoing gamma decay? Nothing. Absolutely nothing. Gamma decay is straight energy. It's essentially X-rays. They're traveling incredibly fast, and they are so small, which is why they have the most penetrating power. It takes several feet of concrete or several inches of lead to stop it. And so, let's see an example. Radium-226 undergoes gamma decay, and it results in radium-226. Nothing changes. That's why they're super dangerous, because it's essentially unlimited energy. That's spooky. That is spooky. However, you're not going to typically see these kinds of problems on your test because there really is nothing to it. Whereas, at least with alpha and beta, you had to know something. But with gamma, not really anything. So let's look at all three of these particles side by side. Alpha, beta, gamma. Alpha getting stopped by the sheet of paper, but beta and gamma cruising on straight through. And beta getting stopped by the small sheet of lead, but gamma cruising straight on through. In fact, it takes a block of lead, a thick block with 3 C's of lead to stop this gamma particle from penetrating. Whew! Yowza. Dangerous, dangerous, dangerous. And now you see why you're wearing that vest in the dentist office. There it is. There are other types of radiation, however, not actually covered in this course. There's such a thing as positron emission, which is essentially the theory is that they take whatever makes a proton positive, the positive essence, and they eject it out. So essentially that proton becomes a neutron, and the positive charge just flies the coop. That's crazy to me. That sounds like some movie type of stuff. I don't know. Then there's also such a thing as electron capture, which is essentially the exact opposite of beta decay. Whereas you snatch that negative electron from the outside and you slam it together with a proton. Positive, negative, combine, neutron. Very, very beautiful. But you're not going to actually see any examples with those, although very, 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 very cool. So let's look at our final 2 terms for the day. Fission versus fusion. Hopefully you've seen these words actually used somewhere. Almost guarantee that you've seen fusion. Hopefully you know that fusion means to combine, which means fission is the opposite. Well, this is how the atomic bomb and how these nuclear reactions that produce energy actually work. If you've seen The Flash, the TV show, which, seasons 1 and 2 are great, and then it just goes horrendously downhill after that, but you still watch! You still watch! Right? Of course you do! But anyways, they have a thing called the particle accelerator. Those exist. Are they gigantic and are they meant for the Flash to go back in time? Absolutely not. What they actually do is they rev up these particles, typically a neutron. They rev them up, till they're going incredibly fast, and then they slam them into the nucleus of one of our radioactive atoms. Pictured here is uranium, which is one of the most commonly used elements for these atomic bombs and our nuclear reactions that we're seeing here. But notice the mass 235, but as the neutron collides with it, they just go ahead and say the mass is 236. Well, this collides with the nucleus at such a force and such a velocity that it causes the atom to split. Fission means to split. And so what does it do? It produces 2 smaller atoms, and then all these other neutrons go flying out as well. It's like shrapnel from a grenade. And what is going to occur? A chain reaction. You split one atom, and this shrapnel that ricochets off from the original atom is going to do the same to all of the neighboring and surrounding atoms. And every time this happens, a ton of energy is released. Hence why we get a lot of energy from these nuclear reactions. Now, fusion, a little different story. Of course, it's completely opposite in nature, still producing a ton of energy. However, very, very difficult to attain here on planet Earth. Whereas fission typically uses bigger atoms, fusion is when very small atoms are going to combine. And the most common example of this is happening in the sun. The sun is a constant example of fusion reactions, all these hydrogens combining to make helium. And then, when the sun runs out of hydrogen to actually react, the sun will die. That's the life cycle of a star. And so this is constantly happening in our sun. And attempts have been made here on planet Earth to do fusion. You need a ton of energy to do it. Hence why the sun is a perfect place to do it, because there's a ton of heat. It's incredibly hot, in case you didn't know that. And it's just the perfect environment. Well, we can't get that hot here on planet Earth. And so there's attempts at cold fusion, which is fusion at lower temperatures. However, not so successful. Not so successful. And then this is last bit of detail. Fusion is combining, fission is splitting, and then here's just little fun facts, right? If you ever have the unfortunate nature, or you witness someone who's undergone chemotherapy or anything like this, this is why you see some of the symptoms that they experience, right? They're having radiation in their body, radioactive material is reacting with them, and it gets to a point where your body simply can't take it. And yes, there have been horrific instances and events in the world's history where people just disintegrated essentially by this just straight energy that's being injected into them. So nuclear energy can be a blessing, but very obviously a curse. So very, very cool to talk about, scary to talk about, and yet quite possibly the future of all of the energy in this world. So that is Unit 3. And the chemistry may begin, ladies and gentlemen. Your background is complete. Your background is complete. Let's get started. Let's get cracking. Let's get going. Have a nice day. See you next time.